Receive a cordial greeting from the IEEE Geoscience and Remote Sensing Society Technical Chapter from the University of El Salvador. My name is Lizardo Arias, a member of the latter chapter. I would like to thank you all for your attendance in our Geoscience and Remote Sensing Congress in its fourth edition with the lemma, The Power of Science in the Hands of Everyone. Today, we have a mini webinar workshop called Deep Learning for Earth Observations Current Status, Challenges and Opportunities given by Dr. Ricardo Delagno. Let me tell you about Ricardo. He is a Brazilian scientist who works as a postdoc researcher at the University of California, Los Angeles, UCLA, and at JPL, NASA, the Jet Propulsion Laboratory. He has a background in environmental engineering, a master in science, and a PhD in remote sensing as well. He studies tropical forest ecology and forest degradation using a range of remote sensing and auxiliary data coupled with a state-of-the-art artificial intelligence methods. Without further ado, we welcome Dr. Ricardo Delagno. You can start the presentation, Dr. Ricardo.
All right. Can you hear me?
Yeah.
Yeah. Thank you very much, Lizardo, for the introduction and also for the invitation. I also welcome everybody that's here to listen. So I guess we can start it. So as Lizardo was telling, my name is Ricardo Dallagnol. I'm a Brazilian scientist, currently working at UCLA and JPL NASA. The presentation today is about deep learning for Earth observation, mostly based on my experience, but also some things I see every day on like Twitter and new trending topics about talking about the challenges and also the opportunities that we have. Let me go here. Oh yeah. So the outline for the presentation is basically these topics. I hope to give like a 30 minutes perhaps talk, and then we can discuss. If you have questions, you send on the chat where you're watching. So we are going to talk a bit a brief introduction about deep learning, and then talk a bit about which problems it can help us to solve using the Earth observation data. Also give some examples based on my experience, talk about challenges, opportunities, and also skills that you can develop along the way to do well on this area. So when I give you these examples and I talk about the applications that I already did, I invite you to think about in your area of expertise, the area that you are working on. Lizardo told me that there are a lot of chemical engineers, electrical engineers, mechanical engineers. There are lots of different areas, and not only Earth observation, but deep learning, artificial intelligence can be applied to like any area. And some of the examples I show here may be used not just for satellite images, but also other images that you can take of your um, study object, study area, and use deep learning to get some data out of that. So let's go. So starting directly from deep learning perspective, the UNet, this thing that you're looking on the screen, is one of the most recent, not very recent, but 2015, yeah, still recent developments of deep learning. So the basis of this is a convolutional neural network. This is the name you find on the papers, CNNs, which are based on the convolution process, the mathematical operation. And coupling these convolutions to the neural network models, they are able to not only understand like one piece of information, let's say one number at a time, but to look at whole images. Look, just as this one that we are looking, that shows some forests, like on a satellite image, and look at the image in a context and extract information similar as a human eye can do. So in this case, for example, it's a paper that we published a few years ago that we wanted to map palm trees on these images. So in the right here, we have the white areas where are the palm locations in this same image patch here. And we train the model to understand these areas that we want to map. And then when the model is trained, it understands the patterns. We can then apply this model to map like a much larger area and get the information that we want. So if you are new to deep learning and this kind of stuff, these are two key words for you to look after: convolutional neural networks and UNet. UNet is one of the CNNs, and it's a very used one in remote sensing. So the basis of this is the convolution, and convolution is basically a small window like this one on the top here that it slides in the image, making multiplications over a larger image. So suppose this one in the bottom is your image that you want to analyze. The one in the top is the window that you are doing this convolution process, and this window, it can do a lot of stuff. So for example, we have this very simple example here, this robot, and we have these two windows, 3x3 matrices that we want to do a convolution over this image. So if we have these values in this window and we go over this image and multiply and summing up the product of the window, we may end up with these kind of outputs. So filters that highlight horizontal lines or vertical lines. And if we do some operation between these two, we get like the outline of this robot. And these filters are the basis of these convolutional neural networks. But the thing for this model is that what if you don't know which filters to use and which features, like which images, which attributes from your images are important? When we want to find, for example, where are the palm trees in this image, it's not just a matter of finding horizontal lines or vertical lines. It's much more complex than that, like what we do when we look at one image. And what the model does, it learns the filters. So this is the incredible part of these models. So we don't say find horizontal lines. we say what are the filters that highlight the objects that we want to find. And on each of these squares on this figure here are layers that we run these convolutions, learning these filters, these small square windows, 3 by 3, and we produce new outputs, new representations of the original image. And on this path that we go down, 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 down here, and then we go up, 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 up here, we downscale the image. Imagine if it's 128 by 128 pixels in the beginning, so it's this size. In the next size, it reduces the size by half, so it's 64 by 64. Next, 32 by 32. Next, 16 by 16. So each layer, each level, it reduces the size of the image in half, but it increases the number of the filters. So for each layer, imagine here 64 of those small windows that we learn, and it increases over time until the middle. And in the middle, the information is compressed. It's like the most compressed part of the information. We have all the features that we want to find from this image over here. But now we don't have the original image anymore. We have 8 by 8 pixels. So it's a very coarse resolution. And now we upsample this information back by doing upsampling and also concatenating, like summing up information from the left to the right. So this is why these arrows. And we like put together the image to the original resolution, but now we don't see like this green, like the colors, like from RGB, true color composite image, but we now have the mask that we want to map. Actually, we first have the probabilities, but in the end, we get this mask. So this is like the high level explanation for this kind of stuff. And when we look at other examples, we see some of the examples of the representations that these models do. For example, if this is an image of the number 4, and in this first layer we have those that we learn those filters, and then they make these representations. So these are the representations after we apply the filter to the image. Sometimes we can understand them, sometimes we cannot understand them, especially when the image is coarser. Like imagine this third column here would be like the center of the UNet. But this is a different model. But this is just to explain that like the information on the bottom of the model, it's more abstract. But then in the end, we have some output. For example, here is a classification of this number 4, and the output of this simple model would be number 4. The highest probability was in number 4. In the end, what we want to do is apply these models to larger images and like delineate objects, map objects, segment objects like palm trees in this case, and apply to a large scale and find where are the locations with more objects that we want to map. For example, the palm trees. And we can associate this to environmental factors, to human presence. Maybe this is important for some communities that can use these palm trees to get food, to get fruits, to get I don't know, anything that they need. So this is one application of that. And one thing that I usually say is that if you can see it on an image, deep learning can map it. So like for example, in this image right here, you can see these objects, which are the palm trees. If our human eye can see that, the deep learning can map it. There's also a footnote to that, is that you need to provide enough examples for it to learn. So, but if you can see it, usually deep learning can map it. And there are a few types of things that deep learning and artificial intelligence can do for us. For example, on a single image, we can do image classification. And this means that this is slightly different than what we learn usually in remote sensing classes when we learn about digital image processing. Like the deep learning community calls and the computing community calls classification, when you say, in this image, what is present? Like there are people, there are persons, there are trees, there are grass, there is sky, for example, and well, there is also a ball here. So these are like words that describe what is present on this image. So this is usually what's called image classification. We can do object detection when we find these bounding boxes around objects that we want to detect. We can do semantic segmentation. This is more usually what we do with satellite imagery. Semantic segmentation for each class, for each object in the surface, we want to map it with a similar class number, class ID. So person is red. Let's say this is number 1. The grass is number 2, and the different color. The trees are number 3, and so forth. And instance segmentation. This is the highest level of this kind of process, where each instance of a given object is mapped on a different ID. So this is person number 1, person number 2, number 3, number 4. So this is much more difficult to do, because sometimes people are just together, and uh, it mixes things up. And this can be important for applications such as building mapping, for example. A building is separate from another building by a different kind of roof, but perhaps the model cannot find that, and I will show some example of that. And now going to the society problems thing, why we want to do all of this Earth observation, remote sensing data, deep learning, because we have a lot of problems in our society that we can use these technologies to help us. And for example, I bring more experience about like environmental stuff, because this is what I work with, but you can use this in the industry for thinking about mechanical engineering. I don't know. You can use some kind of image acquisition system to look at an airplane and check if there is something on the surface of the airplane that's not correct, like something like a fracture in the structure. And you can use the image, and you can couple with some models to find that, and that can help us like an industry innovation infrastructure thing. There are just so many applications, and this is important because we want to be we want to be sustainable, and we want to bring technology to help the world. And Earth observation, big data, is like it can help solve many problems. Like, for example, in urban environments, it can help us to map buildings. It can help us to map solar panels that can be useful for energy. And we can map pools that I don't know why you want to map that, but you can map that. You can map the green covered area in a city, like grass or tree cover, and that also correlates to temperature. Cities that usually have more tree cover, they are cooler. So you can map that. You can find locations on a city that perhaps we need to plant more trees to help with the temperature. We can map natural disasters, and find places that are more vulnerable to disasters. Uh, and also in rural areas, we can map crops, we can map crop types, we can map crop productivity, and that is related to food security. Like, we need to have food production, increasingly food production, because the world is just going up and up in population. We also want to map forests, because climate change is increasing. Extreme events are increasing. We need to absorb more carbon from the atmosphere. So we can map forests, we can map forest carbon, we can count trees. We can look at high resolution images like this. We can even count trees. We can map disturbances on these forests, like natural disturbances, or even man-made, like some place caught in fire that it's not supposed to be caught in fire, and that emits a lot of carbon to the atmosphere. We can calculate that. We can also find places that we want to preserve, perhaps places that we want to restore or make sustainable use, as the example of the palm trees. And this also connects a lot to the market, and I will tell you ahead why is that. And so all of this connects to the to society, to the market, through like price of properties. Like forests are becoming a commodity. Forests are becoming a value. Carbon credits. Cities I wanted to become more sustainable, to produce its own energy, does not depending on um, coal burning or radioactive, I don't know, lots of different energy production. We can make solar energy, for example. And also insurance companies, I have lots of friends that are working right now in insurance companies, because uh, we can map stuff with satellite images. And then you can map, for example, crops. And you can map how well the farmers are doing on their croplands. And if something happens, like a drought, like some hailstorm or something, you can map what is the affected area. So insurance companies are interested in that. So there's a lot of ways that satellite data, earth observation, and the use of deep learning methods are becoming more present in our lives. So, and AI is the new electricity. That who says that is Andrew Ng. It's a like a big guy in artificial intelligence. We use that in our day-to-day lives. We have self-driving cars being developed nowadays, and they need to look in the world similarly as we do. Um, so deep learning can do that. And if deep learning can make a car go into a city and drive by itself, we can definitely look at satellite images and extract interesting information from that. And now this is a nice analogy I like to make, that Earth observation can bring us a lot of data. And here I put some names of satellites and sensors. But in the end, similar to like petroleum, like they are both fuels, but without us doing anything about with to process them, they are just fuels. They don't do anything. But when we put our minds to do that, to look at this image and extract information, or we process this thing in a refinery, we really get something out of it. And really, this is where you guys can help new young people that are coming to the markets. There's so much stuff, so much data, like Earth observations, big data, like so many satellite data. But the important part is you get to know what's your knowledge, what you can bring, and learn some skills how to extract data, and you will have a piece of market. And some informations, some applications with this data I was talking about, some papers that we published. For example, here is about extracting intelligence information from urban areas. Like if we want to map this from satellite images, yeah, we can go on and draw every building on this image. And but this is a small town. Imagine like a big city in Brazil, like Sao Paulo, that has millions of people. Or like right now, I'm living next to Los Angeles. It's huge. It's huge. It's a huge work. If we can train these models to map this for us, like we can speed this thing up very much faster. And there's a lot of methods with deep learning that can do that for us. So this is one method that we developed and published a few years ago. The goal was to segment individual buildings from from satellite imagery. um, and it works quite well for a bunch of these different buildings, but there are always some limitations. Some places that the segments are the model cannot find the edges of the buildings. So there's always places to improve. But you see, in some places that buildings are very close to each other, you have different materials on the rooftops. It can do that. We can improve these models, of course, to do better here. But just for you to know, there are models that can do this. This is the instance segmentation that I was talking about. In precision agriculture, if you have like drone imagery or satellite imagery over an area, you can track cropland producing some crop over time and measure how much what's the yield, how much is it producing over time. And um, if you do that over a big area, you can know how much an entire region is doing about that. And this is useful for the government, for example, to know, oh, what will be the food availability of this specific crop type. So this is very important for government, for food security. Perhaps we have some droughts this year, and we do not have enough I don't know, rice. We need to buy rice from another country to supply for our own country. So this is quite important. And but thinking more on a small scale farmer perspective, if you want to enhance your productivity, you look at these images and you may think, well, where should I put my fertilizers? And this satellite imagery monitoring can help with that. For example, you see on based on drone imagery that one piece of your area is producing more than the other area. And if this production is under the targets that you want to produce, perhaps these are the areas that you need to put fertilizers. And you can use this kind of technology to map and then go into the field and know exactly where you need to put your fertilizers. You don't want to waste them because they cost money. Um, and we tested this methodology, for example, in different scales with drones, with planet scope data at 3-meter resolution, and at Landsat 8 only sensor resolution, 30 meters. And we see they produce quite similar results, showing at least two different zones of productivity, one that produces more, one that produces less. If this is at the level that the farmer is comfortable with, then the farmer can go in and, okay, I need to put some money on fertilizers on this area, and this they can get more money out of this plantation. Now it's just an image about more high-tech agriculture, irrigation, and just to show an example, this is an image from a Brazilian satellite called Cibers. It has some very high resolution image, like I think it's 2 meter, and it's free, by the way. You can see like there are new challenges for croplands as well, like how to deal with these different plantations. Um, so this is just an example. There's no deep learning here. Just found this on Twitter and I find it cool. This is an example of the palm trees I was talking about. This is a paper that we published. It was actually published last week on Remote Sensing Ecology and Conservation Journal. We mapped palm trees on the canopy on the forest of the Amazon at the Brazilian country. And we did that with airborne LiDAR data. So you can see palms at 3 dimensions. So this is looking just from above, and this is the 3D structure. And you can imagine this 3D type of thing, you can use that for a lot of applications. So start thinking about that. If you have some questions about that, you can throw in the chat. We can talk about that. And this is the result why we want to map these palms. Like I had all of these circles, like were different locations that I had this data. They are on LiDAR. So I mapped trees in each of these flight lines, and then I expanded this to the whole Brazilian Amazon. And we find locations that we have more of these palm trees in the forest. So this can be interesting for ecology studies, biology studies, but also for sustainable development. So these are regions that we can see there are a lot of palms in the forest. And also there is a lot of indigenous communities living here. So perhaps they are already using those resources on their livelihoods, but perhaps not. Perhaps we need to invest more, like on government putting money on producing products out of these palm trees, like acai fruits or something. This is another study that we published. The goal here was to map individual tree loss. So looking from one image from one date to another, we wanted to find a tree that was no longer there, like it was cut down or it died naturally. So I did that using both LiDAR data, which captures the height of the vegetation, and also very high resolution satellite imagery, the ones that you see on Google Maps, for example. And we see that both of them shows the tree being disappearing, let's say, from the canopy. And this has many applications. Like, for instance, it can be used to monitor forest concessions. So what's that? Forest concession is a company that is allowed to cut trees inside a national forest, and they do that in theory sustainably. So they can cut up to a number of trees, but we need to monitor that, of course. Like, we want to make sure they are not cutting more than they allowed. So we can use this kind of method to look at these areas that they are allowed to cut trees to manage the forest. But also we may find some areas that are outside of these concessions and show it a lot of tree loss, and then we need to, I don't know, that this can be a forest crime. This can be illegal logging, for example. So just this was a study we published already, 2019, and this is a new study yet unpublished. We are developing some deep learning models to map logging with Planet data. Planet is a satellite that a constellation of small satellites that maps about all the Earth almost daily with 3 to 5 meter resolution. And we are doing some applications in Brazil and Amazon. This is one example inside the same area that I was looking here, but on a bigger perspective. And we have data from the forest concessions on the right, which is our ground truth. So these colors represent years that forest companies went there and cut the trees legally, and we mapped that with our models, and we see the models find those areas, the boundary of those areas, quite well for a lot of these locations. But also they find a lot of different stuff, and maybe there is a new side. Yeah. So this is supposed to be the legal logging part. I was supposed to find stuff over here and over here. I was not supposed to find any logging over here, and this is illegal logging. And this is something that we can take to the authorities, take to the Brazilian Forest Service, and really dig, really investigate, and try to contain these illegal activities inside the national forest, because this is supposed to be preserved. A bit more on this, still on this project. This is a paper I'm producing right now, is to map both logging, this thing you can see on the right, when people go in and cut trees, it leaves this kind of pattern in the image after they log the trees. So these trails and these areas that they put the logs, and also burned forests. So by some reason, these forests are burning. It's not natural. Drought can increase that, but it's not natural. And these models can map those areas, and this can be used for forest crime, like fighting, but also to assess how much carbon we are releasing from the atmosphere. So after everything is done, we can calculate how much carbon we are losing and how we are going down in the whole of climate change. It's sad, but that's kind of the truth. But the good message about this is that we can map these areas, and then we can do something about it. This is a model we had a paper accepted. So this colleague of mine, Fabian Wagner, I'm more of an applications guy. He is more of a development guy. Like, he likes to develop a new model. So he developed this K-texture model, which is, if you had some remote sensing class, you probably know the method called K-means. K-means is not only applied to remote sensing, it's also applied to a lot of classification problems. It tries to find in different, imagine you have two classes of data with a range of values for each one. It tries to separate these two classes without your supervision, like automatically. And what in this paper, what we did, that we use deep learning to do that. So not only we look at one pixel at a time, but we look at the texture of the forest. So like pretty much as we do not look at these images and just see like this is green, this should be a forest, because in a grass like over here, there is also green in a grassland, there's also green in a cropland. But the really what distinguish the forest from the cropland from the grassland is the texture, the different shades of green, the different interleaving of crowns and shadows. So the model kind of understand that and does that automatically. So this is a new model. If you're really interested on artificial intelligence, keep your eye open, follow me on Twitter. You probably see when we share about this paper. Another cool thing, this is not my work, but this is very impressive. This was a work done by Google. They classified, they segmented all catalog of Sentinel-2 images. So Sentinel-2 is a European satellite, 10-meter resolution. It captures data every a few days over the surface of the Earth, and they mapped all the images. So imagine you have for the same area hundreds, almost thousands of images, and they mapped all of them. And if in some dates you may have some clouds or some things that you do not want, you have so many layers of information that you can extract statistics from them. Like imagine you calculate the average class for a given area. So if it's forest or the mode statistic, if it's forest the majority of the time, perhaps it's forest. So it's like a brute force let's say approach to do this kind of um, segmentation, and it's also on Google Earth Engine. So you can readily use this for applications. And for example, this is one example on their website showing the Caldor fire in California. This was a huge fire that occurred in 2021. So this red area is area that was burned, and it's not trees anymore. Now it's like grass. It was classified as grass. So this ends the first part about the status of the deep learning. So I would say that there are new applications every day. If you want to go into deep learning, you can find your niche. So what you know about something, and use that knowledge with some model to extract new information about that. So find what you're good at and use deep learning on some innovative way to find to extract information. And you can also focus on model development, like my colleague likes to do, or just applications using available data, using available models, and just extracting and creating new applications. That's awesome. And also the issue that we face nowadays as young people, issue is not about data. We have a lot of data. The issue is about knowledge and personal skills to really dig into that data and extracting something useful. And that takes us to challenges and opportunities. I'll talk about new markets, knowledge, computation, and skills. And I promise, I think 10 minutes, I will end this. So before we dig on market, I'll give you some quick numbers that I got today because I thought I need to illustrate this. Is that about carbon? Like the global average footprint for any person in the world, like the average, is 5 tons of carbon, so 5,000 kilos of carbon emitted per year. Up to 16 in more developed countries like United States. So we do, like I do that, you do that, everyone do that. We use stuff on our day-to-day. We use cars, we use airplanes, we eat stuff, we emit carbon. There is also force and lots of way nature is taking this carbon down. But imagine population is going up and we are increasing our consumption. So we are going from the 5 to the 16 quite fast. I know for sure when I moved from Brazil to US, I'm increasing this carbon footprint. It's a bit scary, but so what does that mean? 1 ton of carbon is equivalent more or less to 100 trees growing, because one statistic I got is that every tree, like on average, it can capture 10 kilos of carbon per year, while it's growing very fast in the first 10, 20 years. So we need 100 trees growing to offset. So I could say, oh, actually we need more. I need 500 trees to say, okay, I paid my dues. My carbon footprint is 0, and you can be okay with yourself. You're not hurting the world. Companies want to do that nowadays because uh, we are realizing that we are polluting the world. We are increasing temperature. We are going to a place that there's not the light in the end of the tunnel is not the skies, perhaps something coming, and so we need to do that. And this is a new market about carbon credits. So this is one example of carbon credit. It's a company that it's growing very fast, just to show like the price. There's a price on every ton of carbon, $17, and this number last year was $7. So this is increasing like a lot. So companies want to offset their carbons, and they do. How do they do that? Preserving forests, but more efficiently by restoring forests. So this is maybe something important for El Salvador, as it is for Brazil as a tropical country. We have a lot of places that we can do restoration and preservation. I would like the second one to also be accounted. But yeah, this is a growing market, and there's a lot of things going on. But also on a different perspective, on producing stuff, population growing up, we need food. We need to make crops. Crop monitoring, insurance. This is another market that's increasing. I have friends working on that. Every year I have a new friend working for this kind of stuff. um, we need to determine if crops are affected by some kind of factor to know if the food availability will be up or down. Insurance companies want to know that this is a market to explore like right now. um, and the biggest challenge of out of all of these two examples, but all applications to be honest, is domain knowledge and labels. So how do we train our models to do what we want? So this in this example is to have the building masks, like these polygons around the buildings. Another example may be how to map the trees, each tree. So this is where domain knowledge, so how things work, how data works, how data can observe this thing you want to map. This is very important. um, and then comes to how to collect labels to run these models. Like, you can do that manually. You can use someone that knows about the domain you want to map. So this needs collaboration as well. And one thing about this is, which is kind of important, is a difference between traditional machine learning and deep learning, is that when you want to make this kind of maps, you usually need this second column of masks, which are called dense labels or full segmented labels. So it's not just one pixel saying, okay, this in this point in space it's forest. In this point is not forest. It's another thing. For deep learning, you need full labels, dense labels, and this takes time to do. This takes experience, uh, and this can leverage open data sets that has these things. I will show you in a while. Okay, this is one example. This deep learning repository, take a screenshot of this. It's a very good one. I found it a few months ago. It's growing very fast on Twitter. The person that is doing this, it's compiling a lot of applications, a lot of GitHub pages for a lot of different applications. You see here, landslides, fire, smoke, water, vegetation, land use, solar panels, uh, object countings. This can be applied to anything. Ships, boats. You have an image of the sea. You want to count how many boats you have on the shore. I don't know. You can do this for animals. Count how many animals There are some papers that are counting how many elephants there are in Africa, for example. You can do that. This is a very good repository that has data, that has models, that has applications done for each of this stuff. Take a look on this. Another repository is this Radiant ML Hub, LandCoverNet. It has data, human annotated labels based on a consensus score, meaning that more than one people look at the place and said, okay, this is forest, then said, okay, this is really forest. And we need this to make this classifications. We need the labels. So this is quite important and can speed up your application, so you don't need to really draw stuff all over again for a given class. Leverage it, leverage this, use this. And about computation, this takes us to another matter that deviates from the traditional machine learning. It's the CPU versus GPU. You can imagine a CPU, like your processor, your Intel E7 or something. It's like a Ferrari. It's a very fast car. But the GPU, the graphics processing unit that you have or you may have on your computer, the graphics card, it's like this truck. It's slower overall, but it can carry a lot of weight. And we need GPUs for deep learning, because you remember the model, all of these steps, all of those layers, those are like millions and millions of computation. And if you can take each of those computation of those sliding windows and filters and stuff, if you can parallelize those computations, you can imagine one computation on which bag of this, and the truck moves at once. In a Ferrari, you would take many runs back and forth to take the same weight. So we need GPUs for do that. And so further on that, we need cloud platforms. And if you want to work on this field, you need to learn to work with Google Earth Engine. It's becoming like the bread and butter, or in Brazilian we say rice and beans. In Portuguese, arroz e feijão, which is like it's becoming the basic. It's the best platform for data acquisition. A lot of data sets are in there. You just need to get your study area and crop data, and then you can analyze anywhere. Or you can do your analysis in Google Earth Engine. That's fine as well. But this is becoming standard. You need to learn that. But it's moving towards more like Google Cloud platforms and Amazon Web Services. So if you want to apply deep learning, this is the way. You create virtual machines. You run your models in the machines that you need. For one application, you may need more GPU. You create a machine with the GPU you need. And okay, so this is the way to really do it. And all of this data, all of this model, it means that you need big skills as well, not only the big data. And for this, especially for the GIS, for the Geographical Information System, you need to know some software like QGIS. Very important in my work. I use it to visualize data. I use it to collect samples. But I don't use it as much as for processing. You can do that, especially if you're starting, but you should really move towards scientific programming languages like R or Python. Companies are hiring people with knowledge in R and Python like every day, like big tech companies, because you really need to automate your activities. And if you're really working with satellite images, you need to learn about GDAL library. It's the single most efficient thing you can learn about how to handle data in remote sensing that you can learn possibly in the few years. If you learn GDAL, you will speed up your computation like several times. I learn about GDAL every day, new stuff, how to really use it in different ways. It's really good. Also about the thing I was talking about, parallel computing, cloud computing, and data wrangling, which is like, imagine you have a lot of data, but you really need to get the data the way you need to use on a model. So this is called data wrangling. The better you get on that to pre-process your data, the better you're going to produce results. And GDAL really helps on that. And also in analytical skills, the knowledge about your problem, time series analysis, modeling with deep learning are some examples, and also using your creativity to develop new applications. Okay, so heading to the end, some references. I call this the Deep Learning Bible. There's a version for this with Python as well. If you want to really dig in deep learning, it has technical explanations, it has practical examples. You can really learn how to apply these models with this book. I really recommend it. There are also examples in the TensorFlow Kata's websites. Also, this paper, like a review, I like it. You may want to read it if you're interested on that. There's also this website that I made for a workshop last year. It's based on using the UNet model to map crops. So you can enter this and take a look on the video, take a look on the repository if you want to try and run it. I hope it still runs. And more or less that's it. I think I took more than the 30-40 minutes I was thinking about. Hope you enjoy listening. You got something new out of it. If you want to look more on my work, on my papers, take a look at my website. Publication section has the papers. Send me a message, follow me on Twitter, and thank you again for the invitation. And now, if you have some questions, ideas for applications, anything you want to know about my beer on the background, yeah, you can ask me anything. Thank you.
Thank you, Dr. Ricardo, for your valuable presentation. It was indeed a very powerful uh, webinar about all the resources that we can use to our advantages, especially in areas like El Salvador, where we're trying to develop all this kind of geospatial analytics for us. Well, as you said, we'll proceed to the start of the answers and questions segment. If the attendees have any questions related to the workshop, you can write it in the question section, and I'll proceed to read it so that Ricardo can answer it. Also, if you have any questions in Spanish and you wish to ask something to Dr. Ricardo, you can write it in Spanish, and I'll try to translate it so that he can answer it, and also translate his answer as well. So we'll see. Maybe I have a question of my own. Have you worked, Dr. Ricardo, with data sets or any other project related to how solar panels can be used, or kind of like the potential identifying potential zones for solar farms?
I actually saw some application recently. Like they mapped the I think it was the temperature of the in cities to see what were the most, like, imagine a rooftop, which side of the rooftop was more taking more heat, more solar radiance, so that would be more viable for solar panels. Myself, I have not done anything like that, but I imagine temperature data could help with that. Having these building maps, surely you probably need that to know how much area of rooftops you would have available to put these panels. Yeah, but with deep learning, you can definitely map the solar panels. You can map how many of those you have on a city, for example.
Thank you, Dr. Ricardo. I'll have that in mind as well. So we have a question also. It's from Franklin Orlando Jorge Rivera. What is needed to count the number of houses from the detection of the roof area using satellite images and deep learning?
Okay, what is needed? You definitely need very high resolution imagery, which is image with at least at least 1 meter, but no, ideally half a meter, 50 centimeter data, 50 centimeter resolution, because otherwise you can't really see the edges of the buildings. So you would not be able to split between connected buildings. So in that example that I showed, I think that was not satellite imagery. I think that was airborne imagery. Usually cities have airborne uh, data, airborne imagery collected. Um, for example, a city from Brazil, São Paulo, the biggest city in Brazil, they even have lidar data for the whole city. It's a huge city and they have lidar data. You can even tell the height of every house. Like in some states, like in Europe, there are countries that are mapped with airborne imagery and lidar. In California here, I'm starting to understand that also have airborne imagery like across the whole state. It's not a reality for Brazil, at least, like to have those wall-to-wall maps, but it's definitely something like that needs to be brought to the eyes of the governors, to the people that lead cities, like how they can use that information to get information out of how many houses, how the city is expanding to some locations, how many solar panels do we have, uh, you know if the like I remember something. I think here in the US I heard about the government subsidizing, like giving money to people to install solar panels. So if the government want to track how much is that increasing over time, how much the money that we, like, people are paying for the government and they are investing in this, we need to have this data. And besides the image, of course, you need a model. And the one that I showed was the UNet ID. You can take a look on, if you find my publications, my website. It's a publication from 2020, Fabian Wagner, UNet ID. This is a model that we developed for a city in Brazil. It provided a very close estimate of number of buildings than the census that people do in the ground.
Thank you, Dr. Ricardo. We have another question from Federico Ascolani. Hello, what level of programming knowledge do you need to generate this kind of products?
Okay, very good question. I would say there is a steep learning curve because you need to get to learn programming language, but you don't need to learn like C language or Fortran language, those more uh, imagine software development languages. You can learn R, you can learn Python. There are a few new languages, but R and Python are the more consolidated. So these are more scientific programming languages. They are much easier to learn than like C or C sharp or something C++. Like myself, I didn't go to computer science bachelor. I'm an environmental engineer. I did master and PhD in remote sensing. So I've done one class of like computer logics or something. But it takes practice. You need to study it. You definitely need at least like intermediary knowledge. But it's a matter of using it and learning every day. And in the end, you don't need to like um, you don't develop the model, like all the functions and the code inside a model. Like, you don't do that. The models are ready. You basically, what you do, prepare images. You can do that perhaps even on a GIS software. Draw the labels. If it's an application that you don't have the labels yet, like the palm trees I was talking about, like draw the palms. Having that, you create these image patches. You can do that also in GIS, like crop the images for the same locations that you have drawn the polygons. The model itself, like it's basically read image, read a mask, and output the results. There is some knowledge that you need to know to like understand how to make the model to read the images and to output what you want. That's a steep learning curve, as I said, but you don't really dig into the mathematics of like the model itself. It's much more on at the application side. Like really, you don't need to understand how exactly the convolution inside the model is doing its thing. You don't do that. You basically prepare the data, you make a code that reads and output the result.
Thank you, Dr. Ricardo. I guess one last question. Oh, we have another one. It's from Mohammed Boris. Can you suggest, please, an online course for learn more about deep learning and machine learning?
Okay, thank you for the question. Um, I currently don't know a good course for deep learning. I think the guy I mentioned, Andrew NG. Um, I think I will write the name in the chat. You can perhaps put on the screen. I put these two words. Andrew NG is a guy. I I I did his course on machine learning like 10 years ago. It's I think that course is free on Coursera platform. It can help get you started with machine learning in general, but that was like before the boom of the deep learning. It was like 2012. I don't remember when he put the course on, but uh, for deep learning specifically, I think I saw something about they're releasing some new courses focused on like convolutional neural networks and deep learning, but I'm not sure if those are free. And since it's a kind of new, relatively new subject, I don't know much about like relatively easy courses to follow. I still think it's a very ad hoc thing. Like you learn, you apply. There's not a very robust platforms to apply it yet, so it's more or less like we do some this code. They're not very well documented. You have to try and understand that. When you go into that repository that I sent you, for example, um, I'm not sure how clean will be the code, but uh, I think one good starting point is do the course from Andrew and Jean Coursera to get a broad knowledge about machine learning. But the book that I said before from Allaire and Cholet is Deep Learning in R. Deep Learning with R. Sorry, Deep Learning with R. This is a very good book. That not advising that, but perhaps you can find it on the web, and you can read it and start running some simple models like detecting digits, like handwritten digits. Start with that, and you go and increasingly increase the difficulty. I think that's a good starting point.
Thank you, Ricardo. In honor of the time, that would be the last question. So we'll close the answers and questions segment. Thank you all for your participation. We're sorry that we couldn't answer all of your doubts and questions. In honor of us to have such an exceptional talk given by a professional as your vocabulary, Dr. Ricardo, we'll proceed to read the diploma, which reads as the following. Certificate of Participation, IEEE Geoscience and Remote Sensing Society Student Chapter, IEEE GRSS of the University of El Salvador awards this recognition to Ricardo Dallagno for his participation as a speaker at the mini workshop entitled Earth observations, big data, and artificial intelligence applications, status, challenges, and opportunities. The power of science with everyone's reach in Congress of Geoscience and Remote Sensing, CONGRSS 2022, San Salvador, August 9, 2022. It is signed by PhD Manuel Cardona, president of the IEEE section of El Salvador, Andrea Moreno, the student chair of the IEEE GRSS of the University of El Salvador, Doctor in Engineering Carlos Bocasangre, the Counselor of the IEEE GRSS from the University of El Salvador as well, and Dr. Edgar Peña, the Dean of the Faculty of the Engineering and Architecture of the University of El Salvador. We would like to we wish you success in all of your projects to our speaker and to all of the attendees. Thank you so much for all of your assistance. We would like to thank also the unconditional support given by our sponsors, the IEEE GRSS Global, LAGEO, Alpha Geomatics, and the El Salvadorian Association of Architects and Engineers known as ASIA, as well as to all the attendees of this workshop. We would like to invite you to our next activities, which is the webinar called En búsqueda del desarrollo sostenible por medio del ordenamiento territorial, and also creación de mapas con R and ggplot2 part 1. The latter will be given on Wednesday. You can connect with us in our social media as well. Thank you all for your participation. And thank you, Ricardo.
Yeah, thank you very much for the invite.